Hello. So you can see I'm still alive, barely. So the plan is I'll just record this because it's a bit touch and go today, but and hopefully I won't cough through too much of it, and then hopefully by Wednesday and Friday it will be better. And so then let's do this over Zoom so that you can also have questions. So, but today it's just me recording. All right. So we're going through 1.1. So what we're trying to do is go through some of the abstract properties of the real numbers. So we're just defining them abstractly, not necessarily just for real numbers. So for example, we define an ordered set as a set with a relation less than, and this relation is supposed to satisfy trichotomy. So that says that if I have two distinct elements, x and y, then x is less than y or y is less than x. One of the two has to be true, right? So it's called trichotomy because either x is less than y, x is equal to y, or y is less than x. One of the three things has to be true, right? And it's supposed to be transitive, right? So if x is less than y and y is less than z, then x should be less than z. Right, so that's an ordered set, and we define less than or equal to and greater than or equal to in the obvious way for this, right? So less than or equal to is if it's less than or equal to, right? Okay, so some examples of how you can define if you didn't have this ordering. So for example, on the integers, you can define x is less than y as saying, well, x is less than y if and only if y minus x is a natural number. Means it's a positive integer, right? That's one possibility of definition. About rational numbers, the rational numbers are an ordered set. Basically similarly, if y minus x can be written as p over q, where p and q are two positive integers, right? That's one way to define this ordering, right? Another ordered set that comes up quite typically, especially let's say in computer science, is the set of words ordered lexicographically. Right, that's a different set, a different ordering than numbers, but yeah, I mean that's an ordered set. All right, so let's define bounded above and the least upper bound, and bounded below and least and greatest lower bound. So if we have an ordered set S and a subset E, then an element in S, so it's important that this is in S, is an upper bound for E if for every x in E we have x is less than or equal to B. So it could be, I mean, B might or might not be in E. That's not important. It's some element of S, but it is bigger than or equal to every element of E. Right? So that's what's called an upper bound. And if an upper bound exists, then E is bounded above. Right? Similarly for bounded below, it's basically the same exact thing, but for the difference is that x is bigger than or equal to b for all x in E, then b is a lower bound, right? And if a lower bound exists, then the set E is bounded below. Now, we also have, possibly, maybe not, but maybe we do have, a least upper bound. So the smallest upper bound. This might not exist, right? But there could be an upper bound, let's call it B naught, such that any other upper bound B is bigger than or equal to B naught, right? So B naught is an upper bound. And if you take any other upper bound, it's either equal to B naught or it's bigger, right? Then it's called the least upper bound, or the supremum, and we'll write it as sup E, right? And it doesn't always have to exist, right? And similarly, there's a greatest lower bound. So if we have a lower bound that's bigger than all the other lower bounds, or bigger than or equal to, that is the greatest lower bound, or the infimum of E. And we'll write it as inf of E, right? So, and you know, if we have something is bounded above and below, we just say it's bounded, right? And sometimes we'll just say bounded, even if we only care about bounded above and or below. But generally, if we don't care if it, about this, it just has both upper and lower bound, it's bounded, right? All right. So here's an example. So a set E, right? Maybe I'm drawing this on the real line, but it doesn't have to be a real line. But it's an ordered set, so there's an ordering. There's somehow smaller elements and bigger elements, right? So we have a set E right over here, right? And so those are where it's kind of shaded, and all these points, all these over here, those are upper bounds for E. Well, there's only one least upper bound, right? It's the smallest upper bound, right? That's the picture to keep in mind. All right. Now, we did cheat a little bit in the thing. We said, we defined supremum of E and infimum of E as if it was unique, and even though we didn't quite prove it, but it's actually fairly easy to see that it has to be unique, right? So, for example, the supremum, if B and B prime are both suprema, well, then it's they're also upper bounds, right? And so we have that B being the least upper bound is less than or equal to B prime, right? Less than or equal to any other upper bound, and B prime is any other upper bound. Well, the same thing, B prime is the least upper bound, so it's less than or equal to any other upper bound, namely B, right? So that means that B is equal to B prime, right? So there is only one supremum if it exists. It doesn't have to exist, but if it exists, there is only one. All right, so let's look at a simple example. Suppose we have a set with sorry, a set with 5 elements, A, B, C, D, E, and sort of ordered in the usual way. And so that's our ordered set, and our subset E is A and C. Then we have that C, D, and E, right? Because A and C are in the set. Then C, D, and E would be upper bounds, right? And C is the least upper bound, right? Because we have 3 upper bounds, and C is the smallest one of them. So C is the least upper bound. All right. Notice here that C is in E, right? It's a subset of E, but that doesn't have to be. For example, if we look at the rational numbers and we look at all the points that are strictly less than 1, so not equal to 1, strictly less than 1, and that set has a least upper bound 1. 1 is clearly an upper bound. We have this, it's almost by definition, and it is you can easily see that it has to be the least upper bound, but it's not in E, so it doesn't have to be in E. Or you might not have any upper bound at all, right? So, for example, the set of the positive rational numbers has no upper bound. it has a lower bound, 0, but no upper bound. All right. Now, we'll say that an ordered set has the least upper bound property if every non-empty set E that is bounded above, so where at least one upper bound exists, that every such set actually has a supremum, right? So there exists a supremum. It might not be in E, right, but it's some element in S, right? So that's what it means that S has the least upper bound property. For every set bounded above, we have a least upper bound, right? That would be, there could be a similar greatest lower bound property, but it will turn out that we won't really worry about that. So we're just defining the least upper bound property. Sometimes this would be called the completeness property or Dedekind completeness property, especially if we're talking about the real numbers. Right, so for example, Q, the rational numbers, they do not have the least upper bound property, right? So here's an example. Let's suppose that we take the set of rational numbers where x squared is less than 2. I claim that this does not have a supremum in Q. Now, we'll actually use this later on to construct the square root of 2 once we get to that. But basically, the supremum should be square root of 2, and square root of 2 is not a rational number. Let's just prove that fact. So we're being a little vague over here, but let's just prove that there is no rational number that squares to 2, right? So suppose that x is m over n, some rational number, and x squared is 2, right? So suppose there is such a number, because that would be, that would be the natural least upper bound, right? So then, well, if I square this m over n, so m over n squared is 2. I can just do a little bit of algebra. I have m squared is 2n squared. And, a little bit of, I guess, number theory on algebra. If m squared is divisible by 2, that means that m is also divisible by 2, right? Because m squared is, whatever the prime factorization of m is, m squared, just you double the all the primes that you have in m, right, in the prime factorization. So the only way to have a 2 in the prime factorization of m squared is to have a 2 in the prime factorization of m. So n is divisible by 2, meaning you can write it as 2 times some k. And so you can write 2k squared is, but here it's in parentheses, is equal to 2 times n squared, right? Or if I divide by the 2, I get 2k squared is n squared. So n is divisible by 2. So I have m is divisible by 2, I have n is divisible by 2. Now, maybe the way I said it, that's not a contradiction yet, but the way what I wrote here would make it a contradiction. If you assume that m and n, m over n is in lowest terms, then that's a contradiction. I mean, that it's not in lowest terms. There's no way to write it in lowest terms, right? And you can always write any rational number in lowest terms. But here you're saying, well, if there is a square root in the, rational square root of 2, then you cannot write it in lowest terms, so it can't be a rational number. Right. So, all right. So not every subset, not every bounded subset in Q has a least upper bound. So Q does not have the least upper bound property. And this is one of the main reasons for using the real numbers instead of the rational numbers in analysis. We want to be able to take suprema. Really, we want to be able to take limits, and we don't want to worry about, do the limits exist? If they sort of look like they should exist, right? So, if something is bounded above, if we can find sort of better and better approximation for the least upper bound, there better be a least upper bound. So it's one of the main properties of the of real numbers that we'll use, basically, so that we can just take limits, not maybe completely willy-nilly, but that we can take limits if a limit looks like it's going to exist, then it will exist, and we don't have to sort of worry about some sort of weirdness like is square root of 2, does that exist? All right. Now, another property of real numbers that we need is that it's a field, right? So it's not quite a algebra class, but let's quickly go through the definition of a field. So a field is a set together with two operations x plus y and x times y, and it satisfies some axioms, some so-called field axioms. So first is that if I add x plus y, right, that it's defined on every two elements in F, and it gives me an element in F, right? It's commutative. Addition is commutative, right? X plus y is equal to y plus x. Associative. X plus y plus z is x plus y plus z, right? So that's associativity. There's also a zero, so there's an additive identity. That means there is some element, which we'll call 0. So if I add it to any x, I get x back, right? And there's additive inverse. So for every x, there's a minus x. So that if I take x and minus x, add them together, I get this additive identity, the 0. Right? Then there's some multiplicative axioms. By the way, these guys are just saying that it's a it's a abelian group under addition, right? Now, for multiplicative axioms, we have first sort of the same thing. X times y is some element in F for every x and y. It's commutative. It's associative. There exists a multiplicative identity, so a 1, we'll call it a 1. And we're going to assume that 1 is not equal to 0. It's sometimes not everybody's definition of a field includes 1 is not equal to 0. But yeah, for us, we'll mainly be focused on one field. So in our field, it's not equal to 0, and it's really only it's a technicality anyway. Let's not worry about it. We're not algebraists, but basically there is a 1 such that 1 times x is x. You can think about what would happen if 1 equals 0, and also for every non-zero x, there exists a multiplicative inverse, right? So there exists a 1 over x, so that x times 1 over x is 1. So by the way, this says that the non-zero elements of F are an abelian group. And then we have distributive law that says that these operations play nice together. Right, that we x times y plus z is xy plus xe, right? And that's the definition of a field. And there's lots of fields. Q is a field, but there are finite fields. There's lots and lots of fields. There's complex numbers are a field. There's field of rational functions, there's lots and lots of various fields, and a lot of them are useful in various ways. Right? For example, every time you log into your bank, it's probably some finite field being used. All right. So, example, Q is a field, right? Z is not a field, right? The integers, because I have no 1/2 in Z. Right? You have to go to Q to get a multiplicative inverse. So, again, this is not an algebra class. We assume that you know what a field is and sort of the basic properties of fields. So we won't go through, proving everything, trying to do algebra by going back to the field axioms, right? But maybe something that you haven't seen in algebra is what about if you have an ordered set and a field? Now, you could order a field in some random way. So that's not what we're interested in. We're interested in an ordered field, meaning it's a field that is an ordered set, and the ordering plays nice with the algebraic properties. So first, if I have x is less than y, then I can add something to both sides and it preserves the inequality, right? So addition preserves inequalities. And the second property that I'll require is that if I have two positive numbers, so two numbers in my field that are bigger than 0, bigger than the additive identity, then x times y is bigger than 0, right? So basically, one says that the order plays nice with addition, two says order plays nice with multiplication. And, well, I used this word already, right? I mean, if x is bigger than 0, we'll say it's positive, right? And if it's less than 0, we'll say it's negative. And we'll say non-negative if it's bigger than or equal to 0. So it's positive or 0, but it's not negative. And similarly, non-positive if it's less than or equal to 0. Right, so it's not too hard to check that the rational numbers are an ordered field, for example. Okay. Now, let's put together some properties of ordered fields. So, some other very, very basic properties of ordered fields that just follow from the definition of ordered fields. So first, if x is positive, minus x is negative, and vice versa. If x is negative, minus x is positive. If x is positive and I have an inequality, y is less than z, then I can multiply both sides by x, and the inequality is preserved. On the other hand, if x is negative, and I have an inequality y minus z, y is less than z, and I multiply both sides by x, the inequality is reversed, right? Then, if I have any non-zero x, then x squared is positive. So squares are positive in ordered fields, except 0. X, 0 squared is 0. In particular, and it seems like a kind of a stupid thing to point out, but that's actually an important thing to notice. 1 is bigger than 0, right? In any ordered field, right? Not just in the real numbers, not just for rationals, not just in ordered fields that you've seen. Those are basically the only ones that you've seen, really. But in any ordered field, 1 is bigger than 0. Now, if I have two positive numbers, then finding their multiplicative inverses flips the inequality, and they're still positive. So the multiplicative inverses are positive and they're flipped. So if x is less than y, 1 over x is less than 1 over x, and they're still positive. I can also, so this is sort of, I guess, a version of, slightly more general version of 2, right? I might not, if I have x is less than y, and let's suppose they're both positive, I don't have to multiply both sides by x. I could multiply one side by x and one side by y, right? And I would get, so if x is less than y, I have x squared is less than y squared, right, for positive numbers. You get the opposite for negative numbers, but all right. And then if we have sort of similar idea, if we have x is less than or equal to y and z is less than or equal to w, then I can add those inequalities together, right? And the inequality gets preserved, right? So it's slight generalization of from the definition. Okay, so let's prove some of these. Some of these are left as exercises. They're all kind of trivial. So for example, 1, so x being positive implies that by item 1 of the definition, so I have x positive, I could add minus x to both sides, right? So I have x plus minus x, that's going to be 0, is bigger than 0 plus minus x, that's just going to be minus x, which is precisely what I wanted to prove. And the vice versa is the same nonsense. All right, now, if I have y is less than z, I'm proving 2, right? Well, it's the same thing as 0 is bigger than z minus y, right? I can just add minus y to both sides, right? That's part 1 of the definition. And now I could multiply by x, because x is positive. That's again by definition, that should be positive, right? So I have 0 is less than x times z minus y. And so distributive law, and then I add xy to both sides, and I get, I get the conclusion, right? So again, a trivial computation. The opposite, part 3, just an exercise. It's basically the same thing. Let's look at that x squared is positive. So first, suppose x is bigger than 0, x is positive, then I'm multiplying, if I take x squared, it's multiplying two positive numbers, so x squared is positive, just by definition of an ordered field. If x is negative, then we could just use part 3 over here, right? I could just have x and y just be x, right? And z be 0, right? And then what this is, right? It's x times x squared, and x times z, and z is 0, so it's x squared is positive, right? So it basically proves it. It just follows by the previous item. Now let's look at the multiplicative inverses. So let's suppose that I have x is less than y. Right. So first, let's notice that 1 over x cannot be 0. I'll let you think about that. Now, if 1 over x is less than 0, then minus 1 over x would be bigger than 0, right? That's just by part 1. We just proved that a moment ago. So if I have x is positive, minus 1 over x is positive, if I multiply them together, I should get a positive number, right? That should be this, but that means that minus 1 is bigger than 0. And that's going to contradict that 1 is bigger than 0, which followed from this thing, right? So yeah, so that's a contradiction, right? I just add 1 to both sides, for example, right? And I would guess that 0 is bigger than 1, and well, that's not possible. All right. So so that means that if 1 over x is not 0, it's not negative, it has to be positive. And similarly, 1 over y is positive. If I multiply them together, I get a positive number. So we can, we have x is less than y, so I can multiply x less than y on both sides, so by part 2 of the proposition, by 1 over x times 1 over y, right? So, and I get this inequality by part 2 of the proposition. And we do a little bit of algebra, and you find that what's left is 1 over y is less than 1 over x. Now, the last two elements, again, exercises. These are all sort of, equally sort of trivial, right? Now, complex numbers are not an ordered field, and you can see it by this proposition, right? So this proposition shows that complex numbers cannot be an ordered field, no matter what sort of ordering you try to put on it, right? Because the complex numbers are numbers where I have a number I, where I squared is -1, and every ordered field, -1 should be less than 0, but here I have I squared is -1, and any square in an ordered field should be positive, right? So this proposition implies that you cannot order. Doesn't matter how you try to define an ordering on the complex numbers, it's not going to be an ordered field. Okay, maybe could have been part of the previous proposition, but this is actually kind of a common thing to, common argument is if I have a product and it's positive, what does it mean about the two numbers? If x times y is positive, doesn't mean that x and y are positive, but it means that they are of the same sign, right? Either they're both positive or they're both negative, right? So we showed by contrapositive. So what we really show is that if x is 0 or y is 0, so if one of them is 0, or if they have opposite signs, then x times y is not positive. That doesn't mean it's necessarily negative. It's just non-positive, right? I mean, it could be 0 if one of those is 0, right? So, and by the way, this is a good example of being careful when you're negating, negating statements, right? To write down a contrapositive, you have to negate the hypothesis and the conclusion. So you have to be careful when you negate it here. All right. So if at least one of the x and y is 0, then x times y is 0, and so it's not positive. Good. So in that case, we're done. So let's suppose that they're both non-zero, and let's suppose that they have opposite signs. Now, without loss of generality, we could assume that x is positive and y is negative, because otherwise we could just swap the roles of x and y, all right? And whatever we prove, it's going to be the same. So without loss of generality, we can assume that x is bigger than 0 and y is less than 0. So since x is positive, we can multiply y is less than 0 by x, and the inequality is preserved. So we have x times y is less than 0, right? And that's exactly what we wanted to prove, right? So it's a trivial point, but it's actually, that is actually an important one. That if you have a product that's positive, you have to be a little bit careful what it means, right? It just means that both of those things have the same sign, right? Not that they're both positive. Now, before I said that we were talking about the least upper bound property, and that we could have a greatest lower bound property, but yeah, we don't worry about it. And that's really because if we have an ordered field, so it's an ordered set and a field, and it satisfies all those definitions, then we actually we do get whatever the greatest lower bound property would be, right? We get, if this field has the least upper bound property, then for any non-empty set that is bounded below, we have an infimum. So infimum exists. So if there is any lower bound, there is a greatest lower bound. Okay, so let B be a set of the negations of all the things in A. And let's suppose that we have a lower bound for A, right? It's bounded below, so there exists a lower bound. So yeah, let B be a lower bound for A. Whenever x is in A, we get that x is bigger than or equal to B. Or in other words, we get minus x is less than or equal to minus B. Right? This is for all x in A. Well, that just defines the set B. So that means that minus B is an upper bound for B. Now, F has the least upper bound property, right? So there exists a supremum for B, right? B is bounded above. It has an upper bound. Therefore, there exists a least upper bound. Let's call it C, right? Now, it's the least upper bound, so it is an upper bound, but it's also the least upper bound. So it's definitely less than or equal to minus B, right? Which was an upper bound for B. Now, we get, C is an upper bound, so we get that y is less than or equal to C for all y in B. So from that, we get that, we just again go through the definition of what B is in terms of A. That means that minus C, it's the same thing as we're doing over here, right? We just negate both sides over here. That means that minus C is a lower bound for A, right? Right, so minus C is a lower bound for A. And it is bigger than or equal to B, which was just any old lower bound for A. Since it was any lower bound for A, that means that minus C is a lower bound that is bigger than or equal to any other lower bound. Well, that's exactly what it means to be a greatest lower bound. So A has a greatest lower bound, namely minus C. So infimum exists. All right, so that's it for that's it for today. Hopefully I didn't. if I laugh, I cough. So we'll do Zoom on Wednesday.